In this video, I want to show you kind of a simple integration by trigonometric substitution, but I also want to show you a couple ways of doing it. One, where we just kind of recognize the substitution right away and do just a little bit of factoring, and another that is really the same problem and going to get us to the same place, but it also allows us to kind of open up into some new possibilities with some harder integrals. The first thing I want you to do is just notice that with this, hopefully your first inclination is substitution, where you say, well, if I made u equal to 4 plus x squared, du would be 2x. So that's not going to work. So we don't have substitution. I don't like to do integration by parts with something like this. The next thing you say is, well, can I factor it? You can't. If it were 4 minus x squared, we could factor and do integration by partial fractions, but unfortunately 4 plus x squared is not factorable. Well, hopefully you remember from Calc 1, let me just make this little note over here, that the derivative of inverse tangent of x is 1 over 1 plus x squared. Well, that looks a lot like what we have right here. So what I'm going to do is I'm going to factor a 4 out of the denominator. So I'm going to have 1 over, put a 4, then I'll have 1 plus x squared over 4 dx. Just check that real quick, that you look and you say, oh yeah, okay, 4 times 1 is 4, 4 times x squared over 4 is x squared, so they are the same. Well, then I'm going to take that 4 out. It was in the denominator, so it's going to come out front as a 1/4. Okay, then we have 1 on top, and I'm going to write on the bottom 1 plus, and then I'm going to write x divided by 2 squared, like that. And now, if I make u equal to x over 2, then du is equal to 1/2 dx. I can multiply both sides by 2, and that's gone right there. So now I can substitute again. I'm still going to have the 1/4 out front, and I'm going to have 1 over 1 plus u squared multiplied by 2 du. Well, of course, I like to bring those constant multipliers out front. I'm going to bring it like that. So now it's 2/4, 1/2. The antiderivative of 1 over 1 plus u squared is the inverse tangent of u. So this becomes 1/2 the inverse tangent of u plus a constant. I substitute back in. I have 1/2 the inverse tangent of x over 2 plus c. And there's my antiderivative. So it wasn't that bad, but again, I want to show you a different way to do this. We're going to get the same answer, but it opens us up to what if there were some harder things about this, like another multiplier or a square root or something like that. So let me show you the other way, and as I said, that'll lead us into some harder examples tomorrow. So we've got the same integral. Here's what I'm going to start with. I'm going to start by drawing a triangle and looking at the denominator, the part that resembles really Pythagorean theorem. Okay, so I'm going to do this. I'm going to make this angle theta, and I'm going to make this side x, and I'm going to make this side 2. Okay, you're going to see why in a second. So then this side, the hypotenuse, is x squared plus 4. It's a square root. Now, why I've done this is I've created a situation where I'm replicating or kind of looking at Pythagorean theorem to line up with my integral. You may say, well, why? I'll get to that in a second. But again, I just started with theta. I put x. I usually put x across. If at all possible, I put the x on the opposite side. So I knew I just put an x there because Pythagorean theorem then would have x squared. And I put a 2 here because course, 2 squared would be 4. So really, I've set up a triangle where the hypotenuse looks like the denominator of this. Now I'm going to make just a couple little notes below that. I'm going to say that the tangent of theta is equal to opposite over adjacent. The reason I chose tangent was those were the two sides that I was really given in my integral. You know, I was given 2 squared, I was given x squared, so that's why I'm using that. Well, if I know that theta, the tangent of theta is equal to x over 2, then theta must be equal to the inverse tangent of x over 2, just taking the inverse tangent of both sides. Well, I also know through a little cross multiplying back here at the beginning, I also know that x is equal to 2 tangent theta. So that means that the derivative of x, dx, is equal to 2 secant squared of theta d theta. Now again, this way of doing it looks more complicated than what I had before, and it will for this example, but the reason I'm showing you this is because if I added a square root to this, you know, if I had that, then I really would have trouble doing this the old way. Okay, so that's why I'm kind of taking you through this long way. All right, I'm going to go back to the original integral, and I'm going to substitute in for x. I'm going to substitute what x is equal to, okay, right down here, and for dx, I'm going to substitute what dx is equal to. So let's do that. Okay. So I'm going to start by rewriting my integral. 1 over 4 plus, now x we said was 2 tangent theta, so I'm going to have 2 tangent theta squared. And then dx was 2 secant squared theta d theta. Well, you know, I like to pull the 2 out front, so let me do that right away, right there. Let me then rewrite again. So I got 2, I have 1 over 4 plus 4 tangent squared theta, and then I have the secant squared theta d theta. Well, looking at the bottom here, I'm going to factor a 4 out, similar to what I did in the last one. Okay, so I still have the 2, 1 over 4, got 1 plus tangent squared theta, and then secant squared theta d theta. Well, of course, I can pull the 4 out. Since it was in the denominator, it becomes a 2/4. Let me rewrite again. I got 1/2 the integral. Now, let me just, before I do rewrite completely, what we've been looking at the last couple days, remember, is that 1 plus tangent squared theta is actually secant squared theta. So I have 1 over secant squared theta, that's one of our trig identities, multiplied by secant squared theta d theta. Well, these cancel out. So my integral becomes 1/2 derivative of, or the integral of d theta. Well, the integral of d theta is just theta. So I have 1/2 theta plus c. We'll go back up here. Look what theta was equal to. So I substitute back in. Because my original integral was in terms of x, my final answer should be in terms of x. So I'm going to have 1/2 the inverse tangent of x over 2 plus c. Now, this is the exact same answer I got before. The difference is doing it this way, doing it with this inverse trig piece here, allows me to do harder integrals. It allows me to get rid of square roots. All of that we will talk about tomorrow.